This video is part of a course on food physics, and this one has to do with microwave heating, but it's really in two parts. And in the first part that has to do with electromagnetics, that's in 6 sections, and this is the fourth of the 6 sections. This fourth section or the fourth video talks about microwave fields inside an oven. As I said, this one is the fourth of the 6 sections. The other ones are introducing microwaves and their propagation in a slab, talking about food properties, which is the video just before this, and then food factors in energy absorption, which is the video just following this, and then finally the oven factor in absorption. So this one would just talk about waves inside an oven. And here is a fantastic general video on how microwave ovens work, how do they heat. I really recommend you watch this as you see it on the screen. I love it. It's also from my alma mater, and my colleague from my alma mater has shared this with me. So please do watch this one. It's for a general introduction that will really help in the overall and big picture, and it's explained very nicely. Very quick introduction to the microwave oven, and we already talked about what is an electromagnetic wave. So in this case you see this, the red part and the blue part. So the electromagnetic wave has the electric field and then the magnetic field, and it travels in the third direction. And so that's what we talked about electromagnetic waves. So what generates this electromagnetic wave? So in a microwave oven there is this thing called a magnetron uh, on one side that generates these electromagnetic waves. Now those generated waves are fed into the oven, okay, and then in the oven the walls, all 6 walls have to be metallic, and so there is the wave coming in from this side from the magnetron, and these metal walls reflect these electromagnetic waves, the microwaves, and then so the metal walls reflect the microwaves, and so now you have incoming wave and waves from the reflection, and they together form standing waves, and they form this in 3D. We'll talk about that in a second. And then there is the turntable, and the turntable rotates to reduce the effect of the built-in non-uniformity. So let's look at what is causing the non-uniformity. Now, I just mentioned standing waves, so let's spend some time slowly trying to understand what are standing waves, how are they formed. So let's look at this picture here with the red, green, and blue. So the blue waves are coming from the right. So that's like these magnetron generating and sending waves inside the microwave oven, which is called a cavity. Now the green waves here are coming this way. Where are they coming from? That would be the ones reflected inside the microwave oven from the walls. So the green waves are really the blue waves reflected back from the wall. The red one at any location, if you think of any location, then the red one is the addition, where the amplitudes of the blue and green are added uh, to get the amplitude of the red one. Now you look at the red one. Isn't that interesting? Whereas blue is traveling to the left and the green is traveling to the right, the red is not moving at all. It is standing in place. This is why the red would be called a standing wave. So you notice the highs of the amplitude, which in case of heating, it's going to do the most heating, that is at one place. And the lows, where the lows are, here, let's say, it's always staying at one place. And so this is the fundamental issue with heating with microwaves in a cavity. And so now we come back to the cavity. So the cavity has this oncoming waves from the magnetron and then reflected waves. Together they form standing waves, just like it's described on the right. So now you can see with the standing waves, something placed here, it's going to get a lot more heating because that's where the peaks are, and then something here placed here is not going to get much heating at all. And in reality, of course, it's complex because these standing waves, the reflections and the oncoming waves, they are in 3D. But I want to make this most important point, that the heating, the field that does the heating in a microwave oven, it's fundamentally non-uniform, meaning there's going to be places where it's going to be much higher heating and then there's going to be much lower heating. By the way, that was the reason for this turntable. So if the food is rotated, it's going to see the high fields at some of the time and low fields other time, which would tend to average out. So back to the oven, and in this case another oven. It's not a home oven, but still a regular microwave oven, but it was built more for experiments, and we did a lot of modeling and experimental work with it. So I'm sharing with you this one. So again, here the magnetron is here, and so the waves are coming in here, and then again they will get reflected inside. And here is my food sitting in the middle, a cylindrical food. So it's going to set up this 3D standing wave pattern inside. And why I am showing this one is we did a full 3D simulation of this oven, and here is how it looks like. So this shows and the electric fields, the magnitude inside this oven, and you can kind of see these modal patterns. So you see regions of high values, then low values, high values, and so on. It's of course quite complex. By the way, the red stands for higher values and blue is lower. So you can see these kinds of patchy places here, and it is fundamentally quite complex because it's the standing wave forming in 3D. If we cut a section, then we can see the food here in the, so it's kind of cutting a section this way. So you can see the food there, and you can now see inside in this section. Again, you see these highs and then lows. So it's fundamentally non-uniform and complex. Now here we can see the food. So this is the cylindrical food that was here, and this is inside. So even the food also has great amount of non-uniformity, partly from the oven itself, and then it also contributes because of its own dielectric properties and so on. So the point of this slide is mostly to say that it's fundamentally non-uniform and it's quite complex. There's no simple way to describe all these fields, and what you are seeing comes from a simulation of solving the full Maxwell's equations that describe the electromagnetic waves. I showed that the field inside the food was non-uniform in the previous slide. Now I want to show that it's not just non-uniform inside the food, but it also changes with time. And I want to show that using this one electromagnetic simulation of a microwave oven with food. This is oven with food. And what is the food? As you see, it says Tylose cube. This cube, the Tylose, has the properties of beef with the right kind of salt content. It's a cellulose that with the right amount of salt content has the properties of beef. And so think of this as a frozen cube that that blown up looks like this. It's a frozen cube, and by the way, um, these green pieces, these cords, are the fiber optic sensors, temperature sensors placed before freezing, so that we can measure experimentally the temperature. So what I am showing or about to show have been validated experimentally. But what we are doing is doing a electromagnetic simulation where you see this is the port. So waves come in like that, and they get reflected from the walls, and then they form standing wave, and then they form the pattern inside the food as well, which is what we are going to see in a second. Being a frozen material, as it heats, it thaws. And if thaws, as we have talked about in terms of food properties, if a frozen material, meaning water in ice form, does not absorb microwaves that much, whereas the thawed material, water, absorbs microwaves well. So the property of this thing changes quite a bit, and that changes the pattern inside. So we want to look at the field inside this cube, not in the oven, but in the cube. So on the left, what is shown is electric fields on the surface of the cube. So this is not inside, which we'll see in a second. So this is on the surface of, and what you see is how the field on the surface changes as the material thaws, and therefore its dielectric properties change. Now we want to look inside. So if we take a section through the cube, that's what is shown on the right. So this one shows how the field inside the food changes, and of course it also varies with time. Now it shows that the corners and edges are experiencing higher electric field, which is very much a characteristic of microwave oven heating. As the material thaws, it gets more microwave absorbing, like right now, and then the energy gets absorbed all near the surface. so the inside heating is reduced. So we can make one observation for sure, that is the field inside the food is also complex and it changes with position and time during a heating process, and it's particularly obvious when there are huge changes in the dielectric properties of the material, as shown in this case of thawing of a cube of food analog. So here is a summary of this electromagnetic waves inside the microwave oven and their description. We skipped all the mathematical descriptions. There are nice formulas that talk about how the modal pattern can be described inside a cavity, and we skipped all those details, so we pretty much described everything qualitatively, and then our goal was simply trying to see that, look, the pattern, the heating pattern, or the modal, the electric field variation inside a microwave oven is fundamentally non-uniform, and that was our primary goal. So we looked at this kind of qualitative description that the magnetron generates the microwaves, and those waves are fed into the cavity that is the microwave oven, and the waves then reflect from the 6 metallic walls of the cavity, and the reflected wave and the incoming wave form complex 3D standing wave patterns in the oven that makes the electric field fundamentally non-uniform, and we saw pictures of that. And then the pattern inside the food is not completely guided by the pattern in the wave. This is very important. It also depends on the food and oven factors. So the very next video, we're going to get into details of what are the food factors that decide energy absorption inside the food. And the video after that is what are the oven factors, some of the oven factors that decide the energy absorption in the food.